to a couple of different scenarios about what could be going on here. So the first is this idea of the gravitational wave recoil. So in that case, this object here would be the recoiling black hole, recoiling at 1,300 kilometers a second. And this would be the main stellar bulge of the galaxy that's left behind with the black hole ejected from there. Okay? Another option is that you could actually have had a merger of two galaxies and formed a black hole binary, and then a third black hole comes into the mix. And what happens is the lightest of the three black holes gets slingshotted out, ejected. The other two black holes merge. And so this could be a slingshotted black hole from the three-body black hole interaction with the two remaining black holes merged and got left behind here. Now the other scenario, which is actually the simplest and least novel of the three, is that you're just seeing a galaxy merger with two AGN here. And in that case, you still have to explain that broadline offset. And so what it could be is you're seeing AGN outflow from one of the AGN that's producing that large velocity offset. Now that's a really large offset for an outflow, so it would be a pretty unusual outflow system. But that could also be what's going on here. Now, Laura Blecka was a graduate student here who worked on simulations of this galaxy to see if the simulations could place any constraints on which of these scenarios could explain the observed morphology of the system. And so she modeled the recoil scenario, and this is the result from the simulation. So you can see the morphology is pretty similar. It's got that tidal tail. This is the main stellar core, and this would be the ejected black hole right here. So she was able to reproduce this morphology for a couple of different black hole recoil scenarios. So one would be if the black hole got a relatively low velocity kick of 1,400 kilometers a second, so really most of the velocity is along the line of sight here. And so this would have happened, the black holes merge, and then 6 megayears we're seeing the kick where it is now. So the other scenario that produces basically the same agreement with the observations is a large black hole kick of 2,500 kilometers a second that only occurred 1 megayear after merger this far out. So she's able to reproduce the observations with the recoil scenario, but she's also able to reproduce things pretty well with the dual AGN scenario. And so here's the galaxy with the tidal tail again. Here are the two stellar cores. This time there are AGN in each of them. These haven't merged yet. So this is pre-merger. This is not a recoil. And so this would be 50 megayears before the merger. So the simulations say that both of these scenarios, a kick or just a vanilla dual AGN, are possible. And so we're left with these three interpretations. And we still don't know which of these three it is yet, but we're doing more follow-up observations to help clarify the situation. And so coming up in a couple months, we're getting some IFU data for this object at Keck. And so the idea is to map out all the emission in this region and find out exactly where the broadline emission is in here. Is it associated with this? Is it someplace else? So whatever this is, either of these three scenarios, this is going to turn out to be an interesting object. All right, thanks.
So usually some broadlines are offset from the host galaxy even without the kick. There is usually, the narrow line is not always aligned with the broadline. So how do we know that this is not the case here, that perhaps it's just that the broad line is offset from the narrow lines for the same reason that it is in other
so it could be the same. So we see offset broad lines all the time in AGN outflows. So that could be what's producing the broad line offset here. It's just that this is a really huge velocity offset for a broad line. So
usually it's hundreds.
Usually it's hundreds. This is 1,300.
Right.
So it'd have to be a pretty extreme case of an outflow to produce velocity separation like that.
Okay, we have two questions.
So in the scenario where you have the southern one being essentially the kicked AGN with its broadline region, and the northern one being the narrow line region, So that's why you want to get the IFU data to
Yes.
separate that. But even with the resolution, the long slit resolution we have now, it's about an arc-second separation. Do you not see any spatial offset between the broad and narrow line region?
We haven't seen it yet. So we don't know where the broad line emission is yet. So it may be that we're missing it with the slit, and it's not actually associated with that southern nucleus. So that's why instead of relying on slits, we just want to get the full picture with IFU of everything that's going on in the center of this galaxy.
Peter?
Oh, yeah, I was just wondering, so the only thing it takes with it on its journey is its accretion disk, I guess. And so, but it's many dynamical times, the 5 million years. So, and without feeding, is it possible that it survives for that long?
Yeah, so this is the bigger the kick, the longer it'll survive as being observable. And so you have to push the limits of that too. It can't go too far.
Yeah.
It can't go too far for us to still see it. And so
And
that's
it's a point source, I guess.
so the southern source is point-like and the northern source is more extended.
So the typical lifetime of accretion disks would be tens of millions of years, so that's still
Yeah,
would be
so
fine.
it's close to this. Yeah.
So it should be fine.
And the accretion rate, I think, is 0.1 Eddington, so it's not accreting that much. So it's like it can survive for still some time.
Daniel?
In the picture, the stellar nuclei are still distinct. So are there dynamical models that allow the black holes to merge before the stellar cores merge?
Oh, so in the recoil scenario, then this one would be a stellar core, and the southern one would be, it's just a point source.
Can't
So-
you tell from the colors?
From the colors, if there are,
If one is stars and the other is an AGN.
uh,
I'm more surprised that the HST data doesn't clearly distinguish the points. Maybe that just doesn't look, that looks pretty big to be.
yeah, so
Yeah.
Francesca did the modeling.
Yeah, these are HST data, and we have only one band, and so in the other
Yeah, these are
CFHT. We have
A14W.
we have CFHT and other bands, and we cannot resolve the source, but in HST.
Get another band. That's
But
Yeah.
if both nuclei are resolved in HST, then that doesn't match what I understood the video was saying.
If both nuclei are
Source is
resolved in
resolved.
HST.
The question is the southern source actually resolved or not? I thought you were saying that one of them is the nucleus and the other one is just a bare quasar going out.
Yeah.
And then I would expect it to really be a point source even at HST resolution.
Yeah, which this is. The southern source is a point source at HST resolution.
Any other questions for Julie? If not, I should advertise her colloquium today. That would be very exciting, but dual black hole binaries. So thank you very much.
Okay, well, thank you very much for inviting me here to give a short presentation today. Pulsars have now been known for more than 40 years, and people have studied pulsars in great detail. But for our new work, we're realizing pulsars are just some tool to study lots of other things. And unfortunately, pulsar people are not very good at all the other things. And so this is a presentation about my ignorance. I don't know anything about what I'm talking about. But if there's any experts in the room on any of these topics, I would really like to discuss with you. So this project, this talk is all based on data from the Parkes Pulsar Timing Array project. So the Parkes, this is using this Parkes telescope. It's a 64-metre radio telescope in Australia. You can tell it's Australia because of all these kangaroos. And our main goal of this project is to detect ultra-low frequency gravitational waves by using pulsars as a clock, and we look for these variations in the clock, the measured arrival time, as gravitational waves pass through our solar system. So the simple model is we have a galaxy, and Julie's already given me a great introduction to this. they emit gravitational waves. Those gravitational waves propagate through the universe. In our galaxy, there's only one thing of importance, the Parkes telescope. This is not the scale. It's definitely not the scale. And it's not in India either, for some reason. And we've got a pulsar. The pulsar is emitting pulses, and we're detecting those pulses. As space-time gets warped, both around the pulsar and around the Earth, it will mean these pulses will become Doppler shifted. And so the pulses will seem to arrive a little bit earlier or a little bit later than they would if the gravitational waves did not exist. Unfortunately, these pulses are only going to arrive a little bit earlier or a little bit later. If you observe a pulsar for about 5 years, you'll be lucky to see variations of around 10 to 50 nanoseconds. So when you're measuring your pulsar arrival times of 10 to 50 nanoseconds, you have a lot of other things that you have to worry about. And it's all the other things that I'm going to mention in this talk. But first, let's just mention where we are with gravitational waves. We've done a search. These have all been published from the Parkes data in the last 6 months to a year. We've searched for a background of gravitational waves. So these are supermassive black holes all over the universe emitting gravitational waves that turn into like a sea of gravitational waves. We've also looked for individual sources of gravitational waves, and we've looked for gravitational wave memory effects, which happen when the black holes actually coalesce. The summary is we haven't found anything. But that's one, not expected, and two, we're starting to do some astrophysics with our results. This is a measure of gravitational wave amplitude, and we have ruled out everything to the right of where it says PPTA here. And these are various models from models of black hole coalescence and galaxy formation models where they would predict the gravitational wave background. So these here are based on the Millennium simulation and semi-analytic models to work out the coalescence rate and the gravitational wave background. There's various other models. And one, you notice we're cutting into some of these models, so we can already rule out some existing models of galaxy evolution. And two, we're starting to get pretty close to this range where most of the models are predicting a background. So hopefully I'll be able to come back in a few years and we'll either have ruled out all these models for galaxy evolution, or we will have detected gravitational waves. So we're quite close, I think. But to measure these pulse arrival times at the 100 nanosecond or better level, we need a good time standard. We need a good atomic clock. And atomic clocks are not accurate at this level. And so you can turn it around and you can actually use the pulsars to check the atomic clocks. So here's a list of all our pulsars with their sampling. This is from 1995 to almost today. And this is a measurement of how accurate is our atomic clock according to a clock you would build from the pulsars. And you notice this slight variation. And that is actually due to a known steering where they steered International Atomic Time back in around just before the year 2000. And so this was expected, and this line is the expectation. But you also notice we've got about a microsecond offset back in 1997. This may be us saying that the atomic time standard was wrong at that time, and we could see that using the pulsar data. Second effect is these pulsar signals are coming from the pulsar through the interstellar medium. So you can study the interstellar medium. And so this is a plot that we just made a few days ago. This is time across the bottom over a few years. This is the diffractive timescale of measurements of the interstellar medium and the diffractive bandwidth and the dispersion measure of the pulsar. And you notice there was this bump that happened for about 100 or so days. And at the time of that bump, the diffractive bandwidth changed as well. So this is almost definitely an extreme scattering event where we can study how the electron content has changed and get a lot of information from the dynamic spectrum, the scintillation. So we're still studying this data. So that's fine, but unfortunately the solar wind causes effects at our level of timing. And so we're now using the pulsar dispersion measures and rotation measures to study the pulsars as they go behind the sun. And that, as it goes behind the sun, you get huge variations in the DM, and that's due to the solar wind. And this lets us measure the electron density and the magnetic field of the solar corona at around 6 to 10 solar radii. And we're now doing another project with globular clusters where we have lots of very close lines of sight to probe the solar corona on small scales. And while we're talking about globular clusters, I've been chatting with Bulent here about other things we can do with our data, to study the globular cluster dynamics. To predict these pulse arrival times, we don't just need to know the time, we need to know where we are. And we need to know where we are with respect to the solar system barycenter, which means we need to know where the solar system barycenter is. So if the masses of planets were incorrect, the solar system barycenter wouldn't be in the correct place. So we can use the pulsars to measure the position and use that to measure the planetary masses. So these are planetary masses measured by spacecraft. These are planetary masses made independently with just our pulsar observations. And you'll notice they're all consistent, which is a good thing. And for Jupiter, we actually have the best published mass of the Jovian system. And this error bar, this is an error of 4 in this decimal place, means we're sensitive to the masses of the moons going around Jupiter. But to make this more fun, this is where we can also work out where we are on the Earth doing this. Now that's good because we know where we are on the Earth, so we can check it. So this is an observation. We are actually here, or part is there, we're not, where this dot is. And if you observe one observation of one pulsar, we can show that you're somewhere in this red dashed region. If you're somewhere else, if you point at another pulsar, you then say you're in this red region and this green region. And if you throw in a millisecond pulsar, so you've got 3 pulsars now, you can show that you must be at this dot here, and that's about 1 kilometre away from the actual position of the telescope. So that's fun, but then you don't have to be on the ground. So we wrote a paper using the same Parkes data set for what would happen if your telescope wasn't Parkes, but it was on a spacecraft going to Mars. And we had a lot of fun with this. We simulated solar pressure, all sorts of great stuff. And we assumed there was an X-ray, XTE type telescope on board the spacecraft. And we found you could get your position to about 10 kilometres anywhere from a trajectory from Earth to Mars. And the beauty of this is that it will work anywhere in the galaxy. So that's a bit of fun. So just to finish off, what we've currently got is we've got very sensitive data sets now on a load of pulsars. And we're going to combine these with nanograph data. This is the American equivalent project, and European data to form the International Pulsar Timing Array. And I do think we've got a good chance of detecting gravitational waves quite soon. We've got plenty of detection algorithms that have been tested. We've got an approximate idea of the properties of gravitational waves we want to detect. And as I hope I said in my talk, we're doing a lot of other things with our data. But what we'd really like is a guaranteed source of gravitational wave emission. And I'd really like to chat with Julie about some of these ideas, because we don't have one. Everything is based on modelling from black hole formation, galaxy formation, and there's always uncertainties in these. We also need to know, will the source we find be a single source, a background? Will the background be stochastic, or will it have some direction to it? We don't know at the moment. And we also need to know how stable pulsars are on long time scales. And we need a bit of luck. And this is my last picture. This is just a simulation, so there's no real data in here, of a PTA data set spanning for 30 years or so. And I've simulated, in each case, 100 universes. And in those universes, the black holes are in different places, the pulsars were at slightly different distances, and so on. Over time, if we start at timescale here, so the y-axis is the significance of a gravitational wave detection. So on average, last word. On average, it is increasing nicely and smoothly, but in some case, if we're lucky, we can get a 5 sigma detection in just a few years. If we're in an unlucky universe, even after 30 years, we'll only have a 4 sigma detection. So we don't know if we're in a lucky universe or an unlucky universe, and that's a problem for us. And if anyone's interested, I'm here to give a talk tomorrow at the Radcliffe Institute on pulsar navigation. If you're interested in that, go along and hear that. Thank you.
First, I should say that we have a tremendous record today that all speakers took 10 minutes or slightly less.
To a few nanoseconds.
This never happened before, presumably because some of the talks were given by local women. From now on, we'll try to maximize the number of outside people. But with respect to, you showed us a slide where you showed a deviation from the pulsar time sequence and the atomic clocks, and then you said, oh, but something must be wrong with the atomic. why wouldn't you think that maybe you detected something
Detected something like
that would cause a deviation?
in the clock. So one of the big problems that we're going to have to do if we detect a gravitational wave is convince the community that it's really a gravitational wave and it's not an instability in a pulsar or an error in the clocks or something else.
So how do you distinguish?
So we distinguish by not, if you only had one pulsar, you can't distinguish. But if you have lots of pulsars and they all show the same effect, it has to be something at the observatory or the atomic time standard or something. If every pulsar shows a different effect, it will be something on the individual pulsars. So it'll be instabilities of the pulsar. If they show a dipolar effect, it'll be something to do with our solar system. And if they show a quadrupolar spatial signature, that's the prediction from general relativity for a background. So what we're doing is looking for the different spatial correlations in amongst a large number of pulsars. So this signal that you're seeing here with these dots and error bars is the correlated component. It's the same signal in every pulsar. So that's certainly not something that's happening at a given pulsar. It's also not a gravitational wave. It's because it's not every pulsar is showing the same effect. So it's either really is the atomic timescale is incorrect, it may be, or it's something else that's in common to all the pulsars, like maybe all our back-end instrumentation changed at that time and caused some funny effect. But it's certainly some signal that all pulsars see. The other problem with this curve is that all these data points are actually highly correlated, which these error bars don't indicate. So it's a little bit more complicated than just what it looks.
Questions?
For the atomic time standard, there are many independent checks on the Earth. Have you looked at this period of time? To see
Yes.
if there's anything?
So there's plenty of checks on Earth between atomic clocks and between time standards that give at particular countries. But of course there's no check about all atomic clocks, and we can always annoy the atomic clock community by saying, what if there's some effect that affects all the clocks on Earth? There's no way they would be able to find that, because all the checks are with another atomic clock. So that's one possibility, is there is something that really affected all atomic clocks on Earth. But also around this time, they were purposefully steering international atomic time. So steering means they were slightly changing the frequency. And it's very likely that slight variations were made around that time that were not correct. So we don't know exactly yet what caused this, but it was the time when a lot was changing in the atomic time standards.
But you didn't actually check it out with the different places like BIH, USNO, and so forth?
So each individual country's time standard is not precise enough to do this work. So this comes from International Atomic Time, which is the combination of basically all the time standards on the Earth, and comparing it with a BIPM standard, which is the same, but post-corrected when they go back in the future, they think about it and say, well, this clock wasn't as good as we thought it was.
So what happens if you take out the Italian clock? The question
I
of
won't answer that.
I saw someone raising it. Yeah, Doug.
Yeah, so the distribution of dark matter in the galaxy might be clumpy.
Yes.
If a blob of dark matter
Yes.
came coasting through the solar system, what would it look like to you?
It's a wonderful question, and there's just been a couple of papers on that actually from a Russian group using pulsar timing arrays to actually look for clumpy dark matter. So if it's very clumpy, you'll get Shapiro delays effects, where you'll just get a time dilation as the signal passes. And that's what this paper was discussing. But that's basically how people have tried to look for it at the moment. There is no evidence, but you can place constraints on the existence of such clumpy dark matter. But yeah, I mean, any mass that's between us and the pulsar will cause a time delay which should be detectable. It's a great question to work it out.
Other questions? If not, that's it for lunch. Thank you very much.